All right, guys, moving on to 47. We're looking at storage bin. We want to find the dimensions of the largest open top storage bin with a square base and vertical sides that can be made from 108 feet of sheet steel. All right, so open top storage bin that has a square base. So I'm going to give it the same dimension for the base, x and x, and vertical sides. So I'm going to call that h. That can be made from 108 feet of sheet steel. So we only have 108 feet squared of sheet steel, which means that's the surface area is 108 feet. So let's talk about the surfaces that we would have here. We've got 4 sides that all actually have the same dimensions in this case. This is x times h. X times h. And we have 4 of those. So we have 4 xh sides, and we have a bottom, which is actually just a square, and that we gave the side length x, so that would be x squared. So that's our surface area. However, we wanted to find the largest open top bin, and bins are actually measured in terms of largeness, would be its volume. So the volume is what we want to maximize. We've got length times width, x, or x squared, times height. And this is the equation that we want to optimize. So this equation up here, the surface area equation, has to be used, and the only reason we need it around is to get rid of one of these variables, x squared or h. I personally think it's going to be easier to solve it for h and get rid of the h. So I'm going to take this 108, I'm going to subtract x squared. So this is from this equation. I'm going to divide it by 4x, which will give me a value for h. 108 minus x squared over 4x. And I'm going to plug that value into the equation that I want to optimize so that I'm left with only one variable. Volume is x squared times 108 minus x squared over 4x. I'm going to try and simplify it before I get going. So my x squared and my x are going to cancel. I'm going to have x times 108. So 108x over 4, because we still got this 4 denominator. And x times x squared, which is going to be x cubed over 4. This is all from the volume. Once you have that volume equation in terms of one variable, which we do, it's only in terms of x, we can go ahead and optimize it by, we're always going to take its derivative. So this is 108 over 4 times x, will just be 108 over 4, minus, this is 1 over 4 times the derivative of x cubed, which is 3x squared. All right, so we have, and this, I've made this look like, there you go, 1 times 3x squared. Perfect. Okay, we're always going to set this equal to 0. So if this is equal to 0, I can go ahead and add this term to the other side. So 108 over 4 equals 3x squared over 4. They're both over 4, so honestly I can get rid of that. And I get that 108 equals 3x squared divided by 3. And we're going to get 108 divided by 3, 36. I should have known that. 36 is equal to x squared, so x equals 6. All right, it's an optimization problem, so we really want to check that this does what we want it to do. We want it to give it a largest volume possible, so we want to check 6. I'm going to check it in the derivative of volume. I'm going to check a number less than it. So if I plugged in, like, for example, 0, I'd have 108 minus 0, which would just be positive. And then if I plugged in a number bigger than 6, let's say like 10, I'd have 108 over 4 minus 3 times 100, 300 over 4. That's definitely going to be negative. So that does make it a max. All right, and let's just check that we're answering the question. They actually ask us to find the dimensions. So x is the dimension of the bottom, We need the height. Let's go back and use our equation. We knew that h was 108 minus x squared over 4x. So let's plug in 6. That's 108 minus 36 over 4 times 6, which is 24. 108 minus 36 divided by 24 is actually 3. So that would be the best dimensions of this box. All right, moving on really quickly to number 53, the oil refinery question. We have an oil refinery offshore. They gave us a diagram, which was very nice. They told us this is 12, this is x, this is y, and this is 20 minus y. 20 minus y, because the whole thing has to be 20. And they said the rig is drilling 12 feet offshore, 12 miles offshore. It's connected. The underwater pipe costs $40,000. So this costs $40,000, and the land-based pipe costs $30,000. And they want to know what values of x and y give the least expensive connection. Okay, so we want to minimize cost. That's our equation. Okay, so let's think about this. All right, right now cost is always money times length. So this is 40,000 times how long x is, plus 30,000 times 20 minus y. Okay, and this is the equation that we're going to want to optimize, right? So it's 40,000 times this amount and 30,000 times this amount. So we want to go ahead and get rid of one of these variables. We want to get rid of either x or y, so we need to relate them to each other. The only place that we have where they're somewhat vaguely related is right here. So we know that 12 squared plus y squared should equal x squared. Or we can write this as that x is the square root of 12 squared plus y squared. If we use that fact in our cost equation, we can rewrite it so that cost is 40,000 times the square root of 144 plus y squared. 144 is just 12 squared. Plus 30,000 times 20 minus y. All right, here's our cost equation, and the only variable in our cost equation is y. We're ready to go take the derivative. So basically, c prime, the derivative of this, we've got 40,000. It's a constant being multiplied, so we're going to keep it, times the derivative of this, and the derivative of this part right here, we've got something to the 1/2 power. The derivative of that is 1/2 times that something to a power 1 less, which is -1/2. Times the derivative of the inside, which is actually 2y, plus the derivative of this, which is 30,000, times the derivative of the inside, which is -1. All right, take our cost equation, set it equal to 0, and solve. So we've got 0 equals this whole thing. I'm going to add the 30,000 the other side. And right here, I'm gonna have this 40,000. It becomes 20,000. So 20,000. Oh, but then I have to, remultiply it by 2. I apologize. So that's really still 40,000. So we got 40,000 y on top. And on the bottom, we've got this annoying square root of 144 plus y squared, right? All right. You can use your calculator to solve this. If you want to. I'm just going to do it by hand really quickly. I'm going to bring this right up here. So we've got our 30,000, and I'm going to switch these two. So I've got square root of 144 plus y squared is equal to 40,000 y over 30,000. The 30,000, the 40,000, that's going to cancel out. That's going to make it a lot nicer. We got 4/3 y. I'm going to get rid of the square root by squaring both sides. So it ends up that we have 144 plus y squared equals 4/3 y squared. So that becomes 16/9 y squared. Go ahead and we're going to add the y squared to the other side. Subtract the y squared from the other side. So this is subtracting 1y squared. And if I have 16 ninths minus 9 ninths, which would be 1, we're going to have 7. So we got 144 is 7 ninths y squared. All right, we're running out of room here. Get rid of the 7 ninths by dividing by it. I have my calculator. I'm going to go ahead and use that. So I've got 144 divided by 7 ninths. Gives me kind of a funky number, 185.1428. And I'm going to take the square root of that answer. That tells me that y is 13.606. All right, you're going to want to go ahead and check that number, 13.606, which tells us, and then we can go ahead and use that to find the value for x, and we'll be good.